Now the question becomes, how do we do something like the last problem, but instead of using p-values, how do we use rejection regions? Well, let's take a look. You'll still come up with your claim, figure out where it lands as either the null or the alternative hypothesis. Figure out if you have a right-tailed, left-tailed, or two-tailed. You'll still sketch a graph. The difference is when you actually run your test, you're going to be looking at using not a p-value, but a z-value or a t-value. The value that comes out of your test from your calculator, that's going to be what's called your test statistic. It's going to be your z or your t from your t-test or your z-test. Well, that's what you need to see if whether or not that's going to fall into your rejection region or outside of your rejection region. If it falls in your rejection region, you will reject H naught. If it does not fall in your rejection region, you will, be careful, not accept. You'll actually fail to reject H naught. The question is, how do you make your rejection region? Well, your rejection region is going to be made using your alpha. This time you're going to actually use your alpha to make up a rejection region. So the alpha will make up the area in your tail, or tails if there's two of them. And then you can work backwards to actually find the z value or values that make up your tail. And I say z's, but they could be t's, depending on whether or not you are given sigma, the population standard deviation, in the original problem. We'll find z's if we are talking about having the population standard deviation sigma given to us in the problem. If not, then we're going to be stuck finding t-values. Just like before, you'll use your z-test or your t-test, depending on the problem, to find your z or your t. We will also automatically find a p-value. It's just this time we won't use it. Okay. How are we actually going to find the values that make up the rejection region? Well, we already said that we're going to use alpha to fill in the picture in the area in the tail or tails. Well, to work backwards to find a z value, we did this back in chapter 6 and in chapter 7. Then we use the inverse norm function on our calculator, or you can use the normal distribution table. As a warning, remember that the normal distribution table and inverse norm both need an area to the left. Okay. Well, what if we don't have z's and we have t's? We haven't run into this where we're trying to find a t value. Well, if we're going to try and find a t-value, we have something similar in our calculator. There's something called an inverse t function, which is right below your inverse norm on your calculator. The problem with using the inverse t function is it works a little bit differently, but it still wants an area to the left. But there is another option. If you do not have an inverse t in your calculator, you can use the t distribution chart to find the t values as well. Again, the chart does use areas to the left. So either way, whether or not you're using the calculator or the chart, you have to remember that it gives areas to the left. So what table would you use? Well, in your book, it's table A3. And again, Once you have your T values or your Z values that create your rejection region, whether you use the table or the calculator to come up with them, then you'll take your test statistic from either your Z test or your T test and figure out, does it fall in the rejection region you just made? If it does fall in the rejection region, then as we said earlier, then you're going to reject H0. If it's not in the rejection region, then you fail to reject H0. After you figure that out, then you have to figure out what that means about the claim.